Handwriting. It's a personal, unique, and in the age of touchscreen and digital media, more present in our lives than ever before. But can a machine understand it as well as human can? That's what we are going to explore in this video. Welcome everyone, I'm Balkrishna Pandey, and today we're delving deep into the world of machine learning, specifically focusing on handwriting recognition. You may be familiar with MNIST, a database of handwritten digits that has been used to train countless machine learning models. It's a great place to start, but today we're taking things a step further. We're not just going to train a model using the MNIST database, we're also going to use it to recognize my own handwritten digits created right here on my tab. We'll be using Red Hat Openshift Data Science Platform, or RHODS, also called RHODS, for our project. It's an incredible tool that lets us launch Jupyter Hub easily, providing us with a powerful collaborative environment for our exploration in machine learning. It's a perfect for a project like this, and I cannot wait to show you how it works. To do this, we will be using a Keras, a user-friendly neural network library. We'll start by building a simple model, then gradually enhance it to improve our model's ability to predict the handwritten images. This is a hands-on, step-by-step journey into machine learning. Whether you are a seasoned programmer or a curious newcomer, this video is for you. So join me as we explore the fascinating world of handwriting recognition using RHODS and Keras. And also do not forget to join our community www.goglides.dev. Alright, let's get it started. Before we jump into the code, let's talk about the platform we are using today. Red Hat Openshift Data Science, or RHODS for short, is an innovative machine learning platform designed for the hybrid cloud. What makes RHODS unique is its versatility. It offers a fully supported environment where you can establish and follow MLOps best practices. This means that data scientists and developers like you and me can rapidly train, deploy, and monitor machine learning workloads and models. And we can do this both on-premise and in the public cloud. Being an open source platform, RHODS encourages innovation and collaboration. It provides the flexibility to incorporate cutting-edge techniques and technologies into your workflow. This, combined with the stability and support of Red Hat, makes it a powerful tool for any data science project. And the best part, it's easy to get started. RHODS come with an intuitive interface and pre-configured environments like Jupyter notebooks, so you can start coding in no time. So that's the platform we'll be working with today. Let's first see how to install RHODS and launch a new notebooks. Getting RHODS set up is a straightforward process. You start by navigating to Operator Hub in your Openshift console. From there, you search for Openshift Data Science. This is the project. Once you find it, click on the this install button here. This is where you are seeing the overview page where it's talking about the Red Hat Openshift Data Science overview and those kind of stuff. So I'm going to install this latest version 1.28.1 and click on install. Now from here, you can select the channels, and I usually prefer a stable channel. If you want to play with the beta version as well, you can do that. So I'll go with the stable channel at the moment, and you can select the installation mode, all namespace on the cluster or any specific, and looks like this is the default, and I cannot select this version as well. And here is the namespace I'm going to install this. So this is the recommended operator namespace for this particular project. And then I'm going to use approval process as automatic so that I don't have to approve it later manually. So click on install. After a few minutes, RHODS will be installed on your cluster. It's taking time. All right, so as you can see here, the installation is done. Now you can click on the view operator, and here these are all the resources installed as a part of this operator as well. Now as soon as this is complete, you'll see this link being activated here as well. So you'll see this Red Hat Openshift Data Science link. Now you can click on this one, and then it will navigate to this particular project. Then click on this login with Openshift, And I do have enabled two type of authentications. The Kube admin is default one, and GitHub Goglides. This is the one I enabled for GitHub integrations. You can see this. This is the Red Hat Openshift Data Science dashboard. From here, you can launch the Jupyter notebooks, and there are two ways we can do that. One is from application enabled, this launch application. When you click on it, you'll see this form, or you'll see different types of notebook images. We do have TensorFlow 2023 checked out by default. There is minimal Python version as well. You have a notebook image for standard data science project and those kind of stuff. There is another way you can also create the notebook image custom from this notebooks setting page. So here you can pass the repository name and those kind of stuff. And this image will show up in this launch application sections as soon as you create that one. For now, I'm going with TensorFlow. And this is a container size. So there are different size available by default: small, medium, large, X large. With the CPU and memory configuration there, I'm going with small size at the moment. You can also add the environment variables, or you can pass these custom variables to your container image. So for example, if your container image expecting some kind of secrets or env variables, you can set this from here. I don't need this one, so let's delete that. Now, once you click on start the server, so what happens is it will create a container pod in the Openshift cluster. So this is the project. Let me show you here. We're in RHODS notebooks project at the moment. So if you do also get pods, all right, there is only one container running or pod running at the moment, and let's keep watching that one. All right, let's click on start server, and as soon as you do this, you will see new pod is being created on background here on the terminal. And this pod has two containers. It's like health check is filling at the moment, so 0/2 status. And you can also see the logs from the dashboard console itself. So these are the event logs generated. Successfully pull image. So these are the status of that. You can see, I mean, the image is now up and running, the container image or parts are up and running. This is the part running in the background, 100% completed. If you describe this pod, you will see two container images here. So one is, let's see, Jupyter Notebook PandaBK, and there is a OAuth proxy as well. You can also check the logs of those. So if you do here, you'll see two containers, Jupyter Notebook PandaBK and OAuth proxy for authentication. And this is the PVC created Jupyter Hub Notebook PandaBK PVC, which is 20 GB size attached to this particular pod. Now let's click on open in new tab, and it will launch this project Jupyter Notebook PandaBK. And then I'm already authenticated. And from here you can create the new notebooks, you can create terminals, and where you can run the Linux command, and this is the version of that one. And from here you can also create the notebooks, and I'm going to select the default kernel version. It looks like there is others are not available at the moment. So 3.9.16 kernel. You can rename this notebook. So let me call it sequence dash MNIST dash handwriting recognition or something like that, right? So you can call it that. I mean, this is just a friendly name. And from here you can now start testing or writing code. And this is running Python 3.9 version. You can also write the documentation from here. So I'm going to select Markdown, and this is just a test document. You can write the heading like this with the double hash. You can also write the code like with that triple tick, and you can say sample code block and those kind of stuffs. So this is how you write the markdown syntax. Any markdown syntax is supported, and once you commit into Git, it will basically show you that in the markdown format. So let's initialize this project I'm going to use, and once you do ls or git status, you can see this project is initialized. Yep, and then I was expecting this .git folder. Since this is already initialized, now you can add remote repository and commit to the GitHub or any other your favorite Git repository from here. So this is one way you can create the Jupyter notebook, and you can stop for now. I don't have like enough resources, so I'm going to stop it. Then I will show you another process to create this one. Now, if you look at here, I stop that, and then the container or part is immediately gone. So that part no longer available. Now you can go to data science project, and from here you can create the data science project to launch the Jupyter notebook again. So I'll call it Goglides-Dave. And if you go to OC command again, you'll see OC project Goglides-Dave is not present. So you can see OC git ns and grep for Goglides. I do have one Goglides project, but I don't have Goglides-Dave. So when you click on create from this Red Hat Openshift data science project, it will create that namespace as well. So you can see this is created 4 seconds ago. Now let's switch to that project, Goglides-Dave, and keep watching the pod. Now let's create the workbench from here. And then workbench, you can call it anything. It's your friendly name for that particular Jupyter notebook hub cluster. Let's call it MNIST handwriting recognition. And you can select the notebook image. Again, these are default one. You can, once you create your custom image from setting page, you can also select from here. So I'm going to select TensorFlow 2023 versions, and then container size, again, same default value available. I'm going to select the small size. You can also create the new persistent storage, and it's by default selected that name, MNIST handwritten recognition, or if you have your existing persistent storage, you can also select that one. Let's use create the new persistent storage at the moment, and you can also create a data science data connection from here, where you can pass the AWS access key ID, access secret, AWS secret access key, your S3 endpoint. If you have Nuba and those kind of stuffs, you can also use that as a data connection here. For now, it's a new notebook image, so I don't need to create that one. So let's create the persistent storage and create the 20 GB size of that persistent storage. Now let's click on create workbench. Now once you do this, so what happens is it will create a new pod in that particular namespace, and it's calling it MNIST handwriting recognition. It created a stateful set for that one. Now it is starting, and from here you can see the event logs. So this is the status of that particular part. 96% completed. It started container auth proxy. That's a container image, and you can see like 100% completed. Notebook server is up and running. And if you go here, you'll see like part is 2x2 ready status. 44 seconds ago. Now click on open. This will launch a new URL with that name, MNIST handwriting recognition. So it's better to have like the general name instead of using some notebook name here, so that you can use the same notebook server for other notebooks as well, instead of just using for one notebook. So instead of using MNIST handwriting recognition, if you use something else, something general, you can use for other notebook server. This is just a name anyways. So here, once you click on that login, you will see this allowed selected permissions, and this is the first time we're launching it, so you have to authorize that. And it's the same dashboard we saw before using the different method. We created this notebook server. And from here, you can create the notebooks, you can create the console, terminals, you can initialize the Git repositories and those kind of stuff. So same process. We can create one GitHub repository for this one. So I'm going to use this repository. Let's create a new repository in GitHub. Let's call it RHODS Jupyter. I'll call it Jupyter notebooks, okay? That way we can host other notebooks in the future as well, and we can make this project public. So let's initialize that. We don't need to, technically we can add git ignore and readme file as well, so I didn't see any problem there. Let's added a new readme.md file to this particular project. Now we can simply clone this repository from our Jupyter lab here. So what we can do is go to our this newly created Jupyter lab, go to git, and we can simply clone a repository from here, and it includes submodules. I mean, we don't have any submodules, but if you have any submodules in your repository, you can also include that from here. So we'll simply say clone, and I think it will fail because it does not have any authentication mechanism, or it says like host verification fail as well. So let's fix that issue. So what we can do is we can go to the terminal from here, and let's see if we have any SSS folder. So it looks like we don't have any SSS folder. So I'm gonna create the SSS folder for now. Let me make this font a little bit bigger. SSH keygen -t. Let's generate the RSA key pair, and then this will save the key pair here. So I'll use the default so that when it does a git clone, it will actually use that git key pair. I'll use the passphrase as empty, and this generated the key pair. So we do have this private key here and this public keys here. So we should not be sharing our private keys. So I'll simply copy this public key from here. So this is the public key. Do not share the private key. And what we can do is we can go to our Jupyter notebook settings. From here, we can create the deploy keys. Now add deploy keys. Simply paste the keys. That's a public key. You can also allow write access so that we can commit from the Jupyter lab itself. Call it Jupyter lab RHODS, and that's it. So I'll add the key, and this key has access to now write access to my repository as well. So let's confirm this, and it's added now. Now technically I should be able to clone it, so let's perform that clone operation again. Clone repository. Let's use the SSS method instead of username and password. Click on this one and simply say clone, and looks like it's failed again. So host key verification fail. Could not make sure you have the correct access. So that's super odd. Let's see if I can do it from here. Oh, okay, maybe it's waiting on here. So you can see this is already being populated here. So let's click on yes. So yeah, I mean we can do this way. So this already added readme.md file, and that's our readme.md file for this one. And then we clone this using this terminal itself. Now we do have access using SSS protocol. Now next step is creating notebooks. So let's create the notebooks. Call our notebooks. Actually, let's create one folder so that we can organize all the notebooks there. So call it notebooks. So inside the notebooks folder, let's create a new folder again. So call it handwriting recognition. MNIST. So we're going to use MNIST dataset for this one. And inside that, I will create a new notebooks. And then you can call these notebooks anything. So I'll call it 001 generate model. So this job of this module or notebooks is generating the models. And then we'll have another notebooks which we can call it 002 validate model, right? So we'll do some basic validation using MNIST database dataset here in this 001 model itself or notebooks itself, and then I will use my custom handwriting, my own handwriting, and use this validate that model notebooks to validate that handwriting itself. And we don't need this like untitled now, so I'll simply discard this one here. Let's go back. We can delete it. And that's it pretty much. Now, if you want to commit this repository, so what we can do is, let's say if this is gonna work or not, I'm gonna use this method here. Oh, this is actually successfully pushed now. So let's see if this is available here. Okay, so I mean, of course it's pushed, but there is nothing added. So what we can do is, I mean, again, I love terminals, so let me open the terminal. Git status. This is our remote repository. Let's see remote -v. Okay, there is nothing here, so I'm outside the folder. So again, run that command, and you can see this is the location. Let me add, and let me commit this one. Call it like basic skeleton for handwriting recognition model, right? All right, so that's it basically, and it will commit it. So it looks like, I mean, this is the first time we are doing it, and this is, we haven't configured our username and the email. So let's configure that one as well. So we can say git config our email address, and then we can do this one here as well, and my password, sorry, my username. Now if I publish this one, this is already committed. You can see the logs, and this is the log here. So the first one committed from Git itself when we created the README, and this is basic skeleton we just committed from this server. Now if you push it, it will publish this to this main branch, or the commit to this main branch. Now if you refresh this page here, you'll see our, okay, this is one problem. We have to ignore this file, but you can see our notebooks folder has a handwriting recognition MNIST, and then inside that you can see this checkpoint. So I don't like this checkpoint, so we don't need to store that one. So let's fix this issue. What we can do is we can create one ignore, and ignore this folder moving forward. So anything with that one, so we're gonna ignore it. So problem is this folder is already committed, right? I'm wondering what is difference here now. Okay, so anyways, that is committed already, so we want to ignore that. So we have to remove that from our git cache, and the way you can do is you can say git rm cache, and then just do, sorry about that, and then we can do like this one here. It's on the root as well, so we're gonna remove that one. This is a folder, and it's going to remove that checkpoint. And let's do the same for our notebooks folder here as well, and then this is going to remove that one as well. So let's see, now it's deleted and it's tracked now. So if I do git add, git commit, remove folder, and add it dot git ignores to ignore this. Now moving forward, it will not track that folder, and this is gone from here itself. So you can see this is no longer available. Now that's how you can maintain your clean repository. Now let's move on. Now that our environment is set up and we are comfortable with Red Hat Openshift data science, it's time to move on to the fun part. We will dive deep into a classic problem in machine learning: handwriting recognition using Keras and the MNIST dataset. For those unfamiliar, MNIST, which stands for Modified National Institute of Standards and Technology, is a widely used dataset in the machine learning community. The dataset contains grayscale images of handwritten digits, with each image being a size of 28 by 28 pixel. What's interesting about MNIST is that the labels in the dataset are integer values, representing the digits shown in the corresponding image. So for instance, if an image displays a handwritten 3, the corresponding label in the dataset would be the integer 3. In terms of size, the MNIST dataset is divided into a training set and a test set. The training set, which we use to instruct our model, consists of 60,000 images. The test set, used for evaluating the performance of our model, contains 10,000 images. Now let's load the dataset into our Python environment. We will start by importing the MNIST model from Keras dataset. The Keras library provides a convenient interface to load the MNIST dataset directly, which saves us a lot of time and effort. We then call the MNIST.load_dataset function to download the MNIST dataset and load it into memory. This function returns two tuples, the first for the training data and the second for the test data. We then unpack these tuples into 4 separate variables: train images, train labels, test images, and test labels. The image variables contains the actual pixel data of the handwritten digits, while the label variables contains the corresponding integer labels representing what digit is shown in each image. Now that we have loaded our dataset, it's always a good idea to verify whether our data is loaded properly and to understand the size of our data. We can do this by printing the size of our train images, train labels, test images, and test labels. As you can see, the size of our train images is 47,040,000. This number might seem a bit confusing at first, but if we break it down, it makes sense. Each image in our dataset is 28 pixel by 28 pixels, and we have 60,000 images in our training dataset. If we multiply these numbers together, we get 47,040,000. Similarly, the size of our test images is 7,840,000. Each image in our test dataset is also 28 by 28 pixels, and we have 10,000 images in our test dataset. If we multiply these numbers together, we get 7,840,000. We can also understand the structure of our dataset by checking their shape. This gives us a quick overview of the dimension involved. By printing the shape of our dataset, we see that our training and testing images are 3-dimensional arrays. The first dimension corresponds to the number of images, and the next 2 dimensions represent the image height and width in pixel. For our labels, both are 1-dimensional arrays with lengths corresponding to the number of images. Simply put, we have 60,000 28 by 28 pixel images for training, each with a corresponding label, and 10,000 similarly structured images for testing. Let's dive into building our model. In Keras, a model is like a container where we assemble different layers. The Sequential class is a wrapper for the neural network model that treats the network as a sequence of layers. It is a linear stack of layers, and we can simply add layers to it using the add method. We start by initializing a sequential model. This step creates an empty model to which we can start adding layers. Our first layer is a dense layer, also known as fully connected layer. This is because all the neurons in a layer are connected to those in the next layer. Here, we have specified the number of neurons as 512 and the activation function as ReLU, or Rectified Linear Unit, which essentially outputs the input directly if it's positive, else it outputs 0. We have also specified the input shape as 28 by 28, which correspond to the number of pixels in our images, unrolled into a single vector. The final layer of our model has 10 neurons, corresponding to our 10-digit classes, and uses a Softmax activation function. Softmax makes the output sum up to 1, so the output can be interpreted as probabilities. The model will then make its prediction based on which option has the highest probability. That concludes our basic model construction, which is a 2-layer feed-forward neural network. Once we have assembled our model, we need to configure the learning process, which is done via the compile method. The compile method takes 3 arguments: an optimizer, a loss function, and a list of metrics. First, we have the optimizer. This is the algorithm that changes the weights and biases during training. We are using RMSProp as our optimizer. RMSProp stands for root mean square propagation. It is an optimizer designed to speed up the training process. It's specifically suited to dealing with very noisy or sparse gradients. Next is the loss function. This measures how well the model did on training, and we want to minimize this function to steer the model in the right direction. We are using Sparse Categorical cross entropy as our loss function. The reason we use this particular loss function is because our levels are integers. If our levels were one hot encoded, we would use categorical cross entropy. Finally, we have the list of metrics. This is for users to judge the performance of their model. Here, we just want to know the accuracy of our model, that is the proportion of images that are correctly classified. So we pass accuracy to this metrics argument. And with that, our model is ready to be trained on our data. Now, let's try fitting our model to the training data. Our code looks like this. This function will start the training process using our training images and labels. We are telling it to go through the dataset 10 times. That's what epoch equal to 10 means, and for each pass, it should consider 128 images at a time. That's the batch size equal to 128. Now when we run this, we will encounter an error. But why we're getting this error? Well, let's recall how we define our model first. We said model.add dense 512 activation equal to ReLU input save 28 multiplied by 28, which means that the model is expecting each individual input to be 1D array of 784 elements. But currently our training images are stored in a 3D array of say 60,000 28 by 28, which means we have 60,000 images, each of which is a 2D array of 28 by 28 elements. To the model, this looks like we are trying to feed it a bunch of 2D arrays where it expecting 1D arrays. The solution is to reshape our training images so that each image is flattened into a 1D array of 784 elements. Let's go ahead and do that before we try to fit the model again. Let's add one row before fit and paste this code here. We flatten each 28 by 28 image into one dimensional array of length 784. We do this by calling the reshape function on our train image array. As you can see, our array now has 60,000 entries, each of length 784. That's exactly what our model expects. Next, we need to normalize our data. In the context of image data, normalization typically involves scaling pixel intensities to the range 0 and 1. This is important because neural network process inputs using small weight values, and the inputs with larger integer values can disrupt or slow down the learning process. Pixel intensities in grayscale images are represented as integer values ranging from 0 to 255. Here 0 corresponds to black and 255 corresponds to white. The shades of gray fall somewhere in between. So we want to scale these values down to range from 0 to 1. To achieve that, we first convert our data to floating point format with the asType method. This allows for decimal points in our values. Then we divide all the values in the array by 255. Our train images array now contains floating point number ranging from 0 to 1. This normalization steps helps our model to learn more effectively, ensuring that the input values are in a range that's suitable for the weights and biases in the network. Now, let's run the model again with the reshaped and normalized input data. Let's see if we are successful at this time. Notice how it's displaying the accuracy and loss for each epoch. This is important for monitoring the model's learning process. As epochs increase, you should ideally see the loss decreasing and accuracy increasing. If you don't, there could be something wrong with your model or data. But for now, everything seems to be working perfectly. Before we wrap up this section, there is one final but crucial step we should take: saving our model. Training a model can take a long time, especially when dealing with large dataset or complex architecture. By saving our model, we can reuse it in the future without needing to retrain it. Let's go ahead and save our model now using the save function provided by Keras. We will call our model MNIST_v1.h5 and store it in a folder named model. Our model is saved and ready to be used whenever we need it. We have made a significant progress so far, from understanding the MNIST dataset, pre-processing our data, building our model, and finally training it. In the next section, we'll test our model against my own handwriting and evaluate its performance. So stay tuned. Now that we have trained our model, it's time to evaluate its performance. We will be using a separate set of images that the model hasn't seen before. This is our test set. Before we can evaluate the model, we need to pre-process our test images, just like we did with the training images. We reshape the images into the shape our model expects, and we also normalize them. Normalizing the images helps the model to make better prediction because it labels the playing field in terms of color intensities. With this line of code, we are flattening our 2D images into a 1D array because our model expects this shape of the input. Then with this line of code, we are normalizing the images. The images are grayscale, meaning their pixel values range from 0 to 255. We divide each pixel value by 255 to scale it to a range between 0 and 1. Let's run this code. Next, we can finally evaluate our model's performance on this test set. We call the model.evaluate function and pass in our test images and their true labels. This function will return the model's loss on the test set as well as the accuracy. Here are our test loss and accuracy. The loss tells us how far off our model's prediction were from the true labels on average. The accuracy tells us what proportion of the test images our model classified correctly. High accuracy means our model is doing well. We have successfully trained our model, and it's now time for us to put it into the test. But here is the twist. Instead of using the test data from MNIST, we are going to try something a bit more challenging and exciting. I have hand-drawn a set of digits from 0 to 9, each on a separate image. The background of these images is black and the digits are written in the white ink, just like this. I will be uploading these images to RHODS, and we will be using these images to test our model's ability to recognize not just the neatly drawn digits from the MNIST dataset, but also the less uniform handwriting of real people, in this case me. So let's see how our model performs. Let's get these images uploaded and see if our model can successfully recognize my handwriting. Alright, so all the images are uploaded in our RHODS server. Let's test this image using our model. Let's move on to the validation phase, where we will be using our hand-drawn images to test our model. We are doing this with a simple Python script. Let's take a closer look at what each part of this script does. First, we load the trained model from the file MNIST_v1.h5 that we saved earlier. This model will be used to predict the digits in our images. We then define a function preprocess_image that takes in an image path as input. This function does three things. 1. Load the image in the given path and resize it to a 28 by 28 grayscale images to match the format of our training data. It then converts the image into a NumPy array and reshape it into a 2D tensor that can be fed into our model. The reshaping process also flattens the image, turning it from a 28 by 28 matrix of pixel into a 784 element vector. And finally, it normalizes the pixel values by dividing them by 255, just like we did with our training data. This is to ensure that the image data fed into our model has the same scale as our training data. We then use the glob library to gather all the images files from our data directory. These images files are then pre-processed using our preprocess_image function and stacked together using numpy.vstack to form a single numpy array. This array of pre-processed images is then fed into our model's predict method, which gives us the predicted class for each image. The class with the highest predicted probability for each images are selected using numpy.argumentMax. Finally, we print out the file name and the corresponding predicted class for each image. This will allow us to manually check if the predicted class matches the actual digits in the image. So let's run this script and see how well our model does with our handwritten images. As you can see from output, our model isn't performing as well as we'd hoped. It has made some correct prediction, like predicting the class of 0 for the 0.jpg and 5 for 5.jpg. But there are also several instances where it has incorrectly classified the images. For example, it predicted 3 for 2.jpg, 1.jpg, 9.jpg, and many others. These misclassifications indicate that our current model is having trouble differentiating between some of the digits. This could be due to a variety of factors. Perhaps the most significant one is that our model is quite simple. It's a basic neural network with just 2 dense layers. This makes it less capable of recognizing the complex patterns that distinguish different handwritten digits. Another potential issue could be the quality and the diversity of our handwritten digit images. If our images are not representative of the variety of ways a digit can be written, the model may struggle to generalize well. To improve our model, we could take several approaches. First, complexify our model. Our current model is fairly simple. We could experiment with more complex architectures. For instance, we could use convolutional neural networks, CNNs, which are particularly effective for image classification tasks. These networks are designed to automatically and adaptively learn spatial hierarchies of features, which could be very useful for our tasks of handwritten digit recognition. Second, increase training data. The more data our model has to learn from, the better it will perform. We could augment our dataset by introducing more varied handwritten images. This could be achieved by either collecting more hand-drawn digit images or using data augmentation techniques like scaling, translating, or flipping. However, while data augmentation can significantly improve model performance in many scenarios, it's not a one-size-fits-all solution. Some techniques may not be appropriate depending on the context of our data. For instance, in our case, rotation may not be the best choice for augmentation. The reason being some digits can turn into other digits when rotated, like 6 might look like a 9 when flipped upside down. This could introduce unnecessary ambiguity to our model and might actually hinder its learning. Third, implement regularization. Regularization technique can help to prevent overfitting and improve the model's generalization capabilities. We can consider implementing L2 regularization, a popular method which discourages complex models by penalizing the square magnitude of all parameters directly in the objective function. Fourth, tune hyperparameters. Another approach would be to tune the hyperparameters of our model. This includes the learning rate, the number of layers in our model, the number of neurons in each layer, etc. However, this process can be time-consuming and require a good understanding of how each hyperparameter affects the model performance. Remember, model building in machine learning is often an iterative process. It's all about trial and error and constantly refining our approach. So don't be disheartened by initial failures. Let's keep trying to improve our model. Before we continue from here, I want to version control my current work. So let's call our file v1-generate model and call this v1-validate model. Now we can go to Git and save all of the work. So let's add all these untracked images first. These are the data we uploaded in this notebook manually. So let's add all those, and also our changes to the files, generate model and validate model. Right, all it stays. Now we can simply add the summary, what we did in this file here. Let's call it sample custom handwriting, v1 model version, and let's commit that one. All right, so it's committed. Now let's push to remote. Oh, looks like there's some kind of error here. Says failed to push, and looks like it's our SSH permission is wide open, which is super strange. Let's open Git in a terminal, and let's try to push from here. Right, this is a remote repository. Git push origin. Okay, so this shows our IDRSA permission is wide open. Somehow the permission is changed to 0660, so let's change it to 400, and then we should be able to publish from here. There it goes. Now the files are committed to GitHub. We can validate from GitHub repository itself. Let's navigate to GitHub repository, github.com/pandabk, and my RHODS Jupyter notebooks, and you can see I just committed something 1 minute ago. I do have model here, MNIST_v1, and the files also renamed there with the v1 prefix, and this is the data for that one. And also there is a validated model notebooks as well, and I do have data uploaded here also. All right, these are the images. So everything looks good. In version v1 we see a lots of problems, so let's improve this model with the in our version v2. Let's create a new files, call it v2 generate model, and I'll copy some of the code from v1, actually all of the code from v1, and improve some of the part on that v1 model itself. Right, so this is the first section, which is going to load the data. We need a model definition as well, and this model definition will improve slightly here. We'll add regularizer later. Let's move this code base on the top. These are all the import classes from Keras libraries, Sequential and dense layer. We need to compile the model as well, so let's copy these sections. This one has the same optimizer, loss and metrics. Now let's copy this train image section as well. So we need to reshape the images to 1D and they convert into floating point numbers as well, and divide by 255 pixels. Right, this is model.fit. No changes at all. And then we can also copy these test image sections here. This is to validate the model. Now we can finally save this model to different name. So let's maintain v1 so that we can see the progress. So call it v2. Now this looks good. This is the exact code base as model v1. I just remove all the print statement and those kind of stuffs, but this is exact same code base here. So here I'm going to add the regularizers. I'm going to use L2 regularization techniques, and that's it pretty much. So rest is same, so we're loading the same data set, we're using the same sequential model, dense layer with the 512 nodes and 10 nodes here, activation function Softmax. We're also using same optimizer RMSProp, Sparse, Categorical, cross entropy as loss function, and accuracy. We're also converting into 1D tensors, 28 multiplied by 28, and we're feeding into that model. This is converting into floating point numbers and divided by 255 pixels, and we're normalizing it. So everything looks good. We just introduced regularizer. That's it. That's the only change we did in this video model. Now if you run this one, looks like there's a problems. I forget to import the regularizer. Let's add that class as well and rerun the model. Alright, there you go. Now our model is working and it started the training process. And we're going to save this under model directory using name MNIST_v2.s5. We're running it for 10 epochs. Alright, this is complete. Now if you go to the model directory, you'll see MNIST_v2 just created seconds ago. Now what we need to do is let's copy the validate function as well. Call it v2_validate_model. Now here load v2 models, and rest of the part of code is same, so we don't need to change that one at all. So let's run this one. Alright, so now this is the output. Here 0 predicted at 0, 2, 2, 1, 1, 9 to 2. So it's still the model performance is, I mean, it's significantly improved if you compare with the previous numbers or previous model here. So last time it was just predicting 3, or 3 was, I mean, somehow it's biased towards the 3. Now it's improved for sure. You can see, I mean, it's predicting wide range of classes, but it's still not perfect. I mean, you can see 1 is predicted as 8 here, even if 8 is predicted as 8. So it's still some discrepancies here and there, but adding L2 regularization improved this model a lot already. Just one line of code, but it did a lot of improvement here. Alright, so before move on, I want to save this work so that we can see the history later. So let's change, track this in our Git repository. I'll call it v2 model regularizers with L2 regularization technique. And this is committed locally and publish it to GitHub. Alright, now our work is saved successfully. There is nothing left in our directory at the moment. In next section, we'll improve this model even further. In our last iteration, we tried to improve our model by introducing regularization. While that did some improvement, our model still struggled with recognizing the digits from our custom images. In the third version of our model, we are going to leverage a technique known as data augmentation. Data augmentation is a powerful way to increase the diversity of our training set without collecting new data. It works by creating new training examples through different kinds of techniques of the original images, such as rotation, translation, zooming, etc. Before we get into that, let's go through some changes in our code. We are still using same MNIST dataset, but we are reshaping the images to add an extra dimension, which is a requirement for using the image data generator we will introduce later. The labels are being converted to a one hot encoded format, since our last function this time is categorical cross entropy, which works with this format. Our model remains the same in version 2, but we are using the flatten layer to convert our input images into a 1D array before feeding into the dense layer. The image data generated from Keras is what we use for data augmentation. In this case, we are shifting the width and height of the images by up to 10%. This means that during training, our model will see slightly different version of the same images, which should help it generalize better. We are fitting our model on the augmented images produced by the image data generator. We are also specifying the steps per repose as the total number of images divided by the batch size. After training, we evaluate our model on the test data and print out the loss and accuracy. Finally, we save our trained model. This way we can easily load it later to make prediction on new data. Let's go ahead and see how this version of the model performs. This started the training process. We are training for 10 epochs. Alright, so our training process is completed. And if you look at here, we have a new version of model available, which is generated seconds ago. So I copied this validation code as well. So let's run this using this particular model. Well, looks like our model is way worse than before. Looking at the prediction made by our third model, we can observe that the performance has decreased compared to the previous version. While the model has accurately classified some digits such as 0, 2, and 3, it's significantly misclassifying the other digits. The majority of images are being classified as class 8, which indicate that our model might be overfitting to certain patterns in the data that is associated with the digit 8. Using data augmentation and regularization was an attempt to improve the model's ability to generalize, but it seems that our approach is not complex enough to capture the variation present in handwritten digits. In the next iteration, version 4, we will use a convolutional neural network, CNN. CNNs are designed to automatically and adaptively learn spatial hierarchies of features, which makes them well suited for tasks like image classification. This should give our model the complexity it needs to correctly classify the digits in our dataset. Let's see how it will perform. Alright, before we move on to the next iteration of our model, it's a good practice to keep track of the progress we have made so far. In the third version of our model, we introduced the concept of regularization and data augmentation. Somehow, model's performance decreased. The model was still primarily a dense layer network, which isn't the most effective for processing image data. Hence, as we advance from version 3, in version 4 of our model, we are going to implement a convolutional neural network CNN, a powerful tool used widely for image classification tasks. CNNs are well suited to analyze visual data. It has ability to process data with grid-like topology, making them particularly effective for digit recognition tasks like ours. First, we're importing our necessary libraries and module, such as TensorFlow, Keras, and its respective classes. We are then loading the MNIST dataset, just like we did in our previous version. Next, we are reshaping and normalizing our training and test images, converting our labels to a one-hot encoded format. As required by multi-classification tasks, these steps are standard pre-processing steps required before feeding the data into the neural network model. The significant change in version 4 is that we are now using convolutional neural network CNN model instead of simple dense layer based model. CNNs are especially good at picking up on patterns in images. The model is built with Sequential API and consists of Conv2D layer. This is the convolutional layer that will extract features from the input images by sliding a convolutional filter over the input to produce a feature map. We specify 32 filters, and each filter has a size of 3 by 3. In a convolutional layer, filters are the key elements used to scan the input images. When we say we're using 32 filters, it means that the layers will have 32 distinct set of weights or kernels. Each filter is responsible for finding a different kind of features in the input image. For example, one filter might be really good at finding edges in the vertical direction, another might be better at finding circles, and so on. So using more filters allows the model to look for more features in the input images. Each filter scans the images by moving across the image a few pixels at a time, checking a small amount of image each time it moves. The size of area it checks each time is what we call the kernel size, and in this case it is 3 by 3 pixel. This means that the filter is checking a small square of 3 pixel by 3 pixel each time it moves. The choice of kernel size depends on the level of detail you want the model to consider. A 3 by 3 kernel is common in many models because it's small enough to capture important details but large enough to keep the model's complexity under control. Next, MaxPooling 2D layer. A MaxPooling 2D layer is used to reduce the spatial dimension, width and height of the input value. This is done to decrease the computational complexity, enhance the model's robustness to shifts and distortion, and to prevent overfitting. In this case, MaxPooling 2D is applied with a window of size 2 by 2. This means that the input is divided into squares of 2 by 2 pixels, and from each of these squares, only the maximum pixel value is kept and the rest are discarded. The result is a new image with half the original height and width, and it's this downsized image that get passed to the next layer of the model. This pooling operation is applied independently to each depth slice of the input. If the input has multiple channels like an RGB image, the pooling operation would be performed separately on each channel. However, the MNIST dataset consists of grayscale images, so there is only one channel to consider. To sum up, the MaxPooling 2D layer is used to reduce the size of the image, making the model more computationally efficient while preserving the most important features detected by convolutional layers. Next, flatten layer. The flatten layer is used to convert the two-dimensional matrix produced by the previous convolutional and pooling layers into a one-dimensional array or vector. Why do we need to do this? Well, after we have used the convolutional 2D and MaxPooling 2D layers to process the images and extract features, we have data in a two-dimensional form like a grid of pixels. However, the subsequent dense or fully connected layers in our network expect data in a one-dimensional form like a list of values. This is where the flatten layers comes in. It does not perform any learning or transformation of the data itself. It simply restructures the data. It takes the two-dimensional 28 by 20 grid of pixels after being processed through Con2D and MaxPooling 2D layers and lines them up into a long vector of 784 pixels. So the purpose of the flatten layer is to reshape the multi-dimensional output from the previous layers into a format that can be fed into the dense layer for the final stages of the classification process. After the flatten layer have converted the 2D data into 1D vector, we pass this data to a dense layer, sometimes also known as fully connected layer. The dense layer is a neural network that is connected deeply, which means each neuron in the dense layer is connected to every neuron in the previous layer. In this case, the dense layer contains 64 neurons or nodes. Why do we need this? Well, after the Con2D and MaxPooling 2D, layers have processed the images to extract important features, and after the flatten layer has reshaped this data, we need the dense layer to perform the final classification. Each neuron in this layer will learn to recognize different combination of features from the input data, and it will output a value based on what it has learned. The dense layer uses the ReLU Rectified linear unit activation function. The ReLU function is a simple function that allows positive values to pass through unchanged while negative values are modified to 0. It is used in the hidden layers of the network to introduce non-linearity into the model. This non-linearity helps the network learn from the more complex patterns in the data. So the dense layer with 64 neurons and ReLU activation function serves to perform the heavy computation of the model, using the features processed by the previous layers to compute the output of the network. The final layer of this model is another dense layer, similar to the previous one we discussed. However, this dense layer is different in two significant ways. First, it has 10 neurons instead of 64. Each of these neurons correspond to one of the 10 possible classes, digits 0 to 9, that the input image can be classified into. When an image is fed through the network, each neuron in this layer will output a value that corresponds to the probability of the image being that class. The reason we only need 10 neurons in this layer is because we have 10 different classes, 0 to 9 in the MNIST dataset. If we had a different number of classes, we would adjust the number of neurons accordingly. Second, this layer uses a different activation function, the Softmax function. The Softmax function is often used in the final layer of the neural network model that needs to classify input into multiple categories. It turns the output of the previous layer into a distribution of probabilities. That is, each output value from the Softmax function is between 0 and 1, like a probability, and the sum of all the output values is 1. This means that the output of the Softmax function gives us a probabilistic interpretation. The output value of each neuron can be interpreted as the model's confidence that the input image corresponds to the class represented by that neuron. The neuron with the highest output value is the model's chosen class for the input image. So this final dense layer solves a crucial role in the network. It takes the high-level features learned by the previous layers and uses them to assign the image to one of the 10 classes. And it uses the Softmax function to give a probabilistic interpretation of the model's confidence in its decision. Finally, we compile the model using the ADAM optimizer and the categorical cross entropy loss function. ADAM stands for adaptive moment estimation, and it's a popular choice because it's effective and requires little memory and computation power. What makes ADAM unique is that it combines the strength of two other optimizers, AdaGrad and RMSProp. AdaGrad adapts the learning rate to each parameter, which helps if the data is sparse and the parameters have different frequencies. RMSProp also adapts the learning rate, but in a way that's more suitable for handling noise. ADAM takes both these strategies and combines them, which usually results in a good performance on a wide range of problems. Next, we apply data augmentation as in version 3, but this time it's integrated with this CNN model. We then train the model using augmented data and evaluate it on the test dataset. The test loss and test accuracy are printed to see how well the model is doing. Finally, we save this model for future user comparison as we have done with the previous version. Alright, so let's start the training process. The new model should perform better on our data due to the enhanced ability of CNNs to work with image data and the general robustness that comes with a more complex model like this. Of course, we have to be mindful that more complexity can lead to overfitting if not managed properly, but our use of regularization and data augmentation strategy is aimed at mitigating that risks. Alright, so our model training process is finished. So let's test with our test script. So I'm going to use the same version v4. We can observe significant improvement in this version. By switching from a dense layer network to a convolutional neural network, we managed to make our model more attuned to the complexity of images, resulting in better performance. The model now performs quite accurately, correctly classifying a broad range of digits from 0 to 9, unlike our version 3, where we saw a strong bias towards a single class. Each line in the output represents one image from our dataset, and the predicted class is what our model believes the digit in the image to be. We can see that from images like 0.jpg, 2.jpg, and 4.jpg, the model has correctly identified the handwritten digits. However, we still have instances of misclassification like the one with 7.jpg, which is predicted as class 8. This shows that while our model's performance has enhanced with the use of convolutional neural network, it is not perfect and there are still areas where it can be refined. There are several ways we can improve the model in the code. For instance, as we transition from version 4 to version 5, we'll be fine-tuning our CNN model by integrating additional layers. Specifically, we're adding another Com2D layer, which helps in extracting more sophisticated features from the images, and an extra MaxPooling 2D layer, which assists in reducing the output dimension from the preceding layer, thus making the model more efficient. By layering these components, we aim to augment our model learning capabilities, potentially leading to better identification and classification of the handwritten digits in our dataset. Alright, let's train our v5 model with these changes. We're saving this model here in MNIST version 5. While this is training, I want to change the naming convention here for v1 and v2 as well. So let's copy this code here. And we can safely delete this one now. Let's do the same for this one as well. Alright, so our V5 model is already trained and saved in the folder. This is the just produced model. Alright, so let's validate this model. In this final version of our model, we're seeing great results. Every number from 0 to 9 is getting correctly recognized, no matter which file it comes from. This is a big step up from the previous version. The extra layers we added in this version have made the model a lot smarter in recognizing different ways of writing numbers. So we have gone through quite a journey together. We started with a basic model and then we made it better step by step. We tried out different techniques like making the data more varied, reducing overfitting, and changing the model structure to a convolutional neural network. And then in the last step, we added even more layers to make the model even more accurate. To wrap up, I want to say that we have learned a lot together, but there is so much more out there in the world of deep learning to discover. So keep experimenting, keep learning, and most importantly, have fun doing it. Also, do not forget to join our IT community www.goglides.dev. Subscribe to YouTube channel as well. Thanks for joining me on this journey, and I look forward to our next adventure.